Hello everyone, this is tutorial number 4 on digital signal processing. In this tutorial, we will cover some questions on discrete time processing of continuous time signals and also some questions on upsampling and downsampling of the time period. So let us start with question number 1. In question number 1, first of all, we have been given this figure, which we've already seen a few times before, where we have a discrete time system and the input is some continuous time signal and the output is also some continuous time signal. And this discrete time system performs some operation by first converting this signal into a sequence, and then again the result output sequence is converted to continuous time. So it is given to us, the question says, consider the system in the above figure with xc omega equals to 0 for omega greater than 2 pi into 1000. So it is a band limited signal, and the discrete time system a squarer, which means that this particular block over here is a squarer, which means that its output will be the squared of its input. We are asked what is the largest value of t such that the output signal is the input signal xc square t. So what is the largest value of t so that this overall system performs like this? It performs this operation. Okay. So let's see. So first of all, we have yn, which is equal to x square of n. So if we look at this sequence, this process that this discrete time signal is performing, then it is basically just the product of two sequences x of n. Now, if we look at this in the frequency domain, then by taking the DTFT of both sides, clearly in the right hand side, it will be the convolution of the frequency, the spectrum of x e raised to the power j omega with itself, because in the frequency, because in the time domain it was a product, so in the frequency domain it will become a convolution. Now, let's say y e raised to the power j omega, or clearly y e raised to the power j omega will occupy twice the frequency band that x e raised to the power j omega does, right? Because if we have convolution and let's say this signal is band limited between some frequency omega, and this obviously then this one will also be band limited at some frequency omega, then when we take the convolution, then those limits of frequency will get added up, right? So omega plus omega will become 2 omega, right? So that is what this statement means. So whenever we convolute, the limits get added up for the frequency, right? So if the signal y e raised to the power j omega, or the frequency spectrum of y is between minus pi to pi, then for x it would be the half. So x e raised to the power j omega will have a spectrum between minus pi by 2 to pi by 2, right? So we have been given that the continuous time signal x is band limited at this frequency 2 pi into 1000, right? And then we can clearly say that that means that this 2 pi into 1000 is this is capital omega, and we know the relation between capital omega and small omega. Uh, so small omega scaled by t is equal to the capital omega. So we can substitute it here, and this small omega will be nothing but omega is equal to pi by 2, because that is the upper limit for x, right? So we can substitute it here, and using this we can find out this t simply by solving this inequality, and that will give us t is less than equal to 1 by 4000. So this is the time period that is largest possible. So it is largest possible because we have taken it corresponding to this omega equals to pi by 2. And so any t that is less than equal to 1 by 4000 is, so t is equal to 1 by 4000 is just t is equal to t less than equal to 1 by 4000 is the answer. So this is the largest time period. Coming to question number 2, this time we have been given this figure. Again, in this case, this is similar to the what we had last time. In this case, this discrete time system is actually a downsampler, which will decrease the time period by a factor of 2, right? And the rest is the same. We have a sampling time of t in the for the C to D converter, and for the D to C converter, the sampling period is t dash. Okay. So the first question says that assume that the input has a Fourier transform such that xej omega equals to 0 for omega greater than 2 pi into 100. So again, the input signal is band limited. What value of t is required so that x e raised to the power j omega, which is the DTFT of this sequence, is between pi by 2 to pi. This is what we have to do in the first part. So let's look at the first part first. So obviously x of n is x of c sampled with a time period of t, and y of n will be nothing but x of n with the time period downsampled by a factor of 2. So y of n is nothing but x of 2n, right? We know this relation between the frequency in the discrete time and the frequency in the continuous time. Now, if you look at the signal, so the signal x has lies between omega from pi by 2 to pi, which means that its bandwidth is equal to pi minus pi by 2, right? And we can simply equate it with the fact that in the continuous time, omega is band limited at 2 pi into 100 in order to find out the value of t. So omega into 2 pi into 100 times t, that is capital omega times t, is simply equal to the small omega, which we desire, right? This is the desired x. So we can solve directly for t, and t will be equal to 1 by 400. Okay, so this is the first part. In the second part, we have to find out this t dash so that yct is equal to xct, or basically we have to find out a t dash such that we can completely reconstruct the signal and the output signal is the same as the input signal, right? So that means that t dash has to compensate for the effect of this downsampling of 2. All right. So first of all, let us look at the spectrum of x e raised to the power j omega. So x e raised to the power j omega is basically the signal that we have obtained after sampling. So its magnitude will become 1 by t. The amplitude is 1 by t, the amplitude of the spectrum, right? And we already know that omega, small omega, is capital omega n times t. Capital omega n is the input sequences band limit, right? This we already know, and we have already calculated t as 1 by 400, right? Now we pass it through this block, which is the block of downsampling of 2. And when we do this, the amplitude will become 1 by mt, that is 1 by 800, right? Because m is 2. And what happens to the frequency axis? The frequency axis will get scaled and by a factor of m. So instead of omega n t, now it will become omega n into m into t, right? Where m is 2. So omega is, if we calculate this omega, it will simply be equal to capital omega n into 1 by 200. Now, if we have to completely reconstruct the signal, so we have to take into consideration this fact that the frequency axis has expanded by a factor of 2, right? If we want to completely reconstruct, then that means that the spectrum of the output must be the same as the spectrum of the input, which means that in one way, the one way to look at it is that this omega should be less than or equal to pi, so that there is no aliasing, right? So we can say that the if we look at the Nyquist rate, we simply know that omega should be less than pi in order to completely reconstruct, right? Or in other words, we can simply say that this omega n into 1 by 200 is the frequency, and we should select the time period of reconstruction in a similar manner to compensate for this scaling of frequency axis or expansion of frequency axis. So we can simply equate omega and t dash, that is the frequency. So omega and t dash is the frequency, or this t dash is actually the period at which we want to reconstruct the signal, and we can simply equate it with the frequency of the signal after downsampling. And from this, we can find out that t dash is equal to 1 by 200. So in this way, this is the t dash if we want to completely reconstruct the signal after considering the fact that the frequency has been, or the frequency axis has expanded by a factor of 2 due to downsampling. Okay, coming to question number 3. In this one, we again have this overall system. On one hand, there is an ideal C to D converter. One hand, we have an ideal D to C converter, and there is an upsampling block here. Okay, so let's see what happens. What this question says. So the question says, consider the system shown in the above figure. The frequency response of the input to the system and the discrete time LTI system are shown. So we are shown here in these two figures, the input, the frequency response of the input. So the input is band limited at pi by t, and the frequency response or the impulse response, which is this one, right? So this impulse response corresponds to this block over here, h e raised to the power j omega. It has a frequency response that looks like this. First of all, in the first part, we are asked to sketch the Fourier transform of x, xn, xe, ye, and yc. So let's first do this. Okay. So let's first look at this diagram again. So xn is basically nothing but xe sampled with a sampling period of t. Xe is obtained by upsampling xn by a factor of 4, and ye is what we obtain after passing xe through the filter whose frequency response is this. And finally, we again have an ideal D2C D2C filter to reconstruct, and it has a time period of t by 4, where t is the time period at which we originally sampled the signal. Okay. So first of all, let us sketch these signals. X e raised to the power j omega, which is Fourier transform of x of n. So clearly, it will have an amplitude scaling of 1 by t. And since the signal was originally, the input signal was band limited between minus pi by t to pi by t, and we have scaled with a factor of, we have sampled with a time period of t, then clearly the DTFT of the sampled signal will lie between minus pi to pi, right? Which we can also compute by saying that omega is equal to capital omega times t. Okay, so this is x e raised to the power j omega. Then we have to find out x e raised to the power j omega, which is the signal that we have obtained after passing through the upsampler. So what happens is that the signal, the frequency axis will get scaled by a factor of 4. So this pi here will become pi by 4, and it will be scaled down. Similarly, this minus pi becomes minus pi by 4, and so on. The complete frequency axis will be scaled. Right. Now the third thing is y e raised to the power j omega, which corresponds to after we have passed it through the through this filter. So again, look at this filter. Clearly, it allows the frequency spectrum between pi by 4 to 3 pi by 4 and minus 3 pi by 4 to minus pi by 4 to pass. The rest of it will not appear in the output. So since we have this from pi by 4 to 3 pi by 4 and from minus 3 pi by 4 to minus pi by 4, this part of the spectrum will appear in the output. So as you can see here, this is the output. And also note that the amplitude is scaled by a factor of 4, right? Which is obvious because this h e raised to the power j omega has a factor of 4 here. That's why. Okay, so this is y e raised to the power j omega. Okay, finally we have to plot the spectrum of y c, which is the reconstructed output. So once we have got y e, y c j omega is nothing but sampling of y e with a factor of with a time period of t dash. T dash is d by 4. So again, there will be the amplitude will be scaled by a factor of 1 by t or 1 by t dash. So 4 by t becomes just multiplied with t by 4, and that's equal to 1. And pi by 4 multiplied with 4 by t becomes pi by t, and so on. So the frequency axis will also get scaled accordingly by a factor of t dash. Okay, now let's come to the second part of this question. It says, if we consider the general case of the input being band limited, then if we wish to express the output in terms of the input, the DTF, the CTFT of the output in terms of the CTFT of the input. And then we have to express the continuous time signal YCT in terms of the continuous time input XCT. So let's see. So the input that was given to us is XC, has a frequency spectrum, something like this, between minus pi by t to pi by t. This is given to us. And YC of j omega is this. This is the output. So this is the output and this is the input. We have to write the output spectrum in terms of the input spectrum. So clearly, if we move this spectrum by an amount of 2 pi by t, then this minus pi by t will become pi by t, and this pi by t will become 3 pi by t. Similarly, if we move it in the other direction by again 2 pi by t, then we will get this part. So that is what we have to do. We can say that YC j omega is simply XC j. Now I have shifted the frequency omega, capital Omega, by a factor of 2 pi by t. And then again added to it a factor of 2 pi by t. So here there is a minus of 2 pi by t to obtain the first part and plus 2 pi by t to obtain the second part. And in this way, I can write y in terms of x. Now, when we have to write down the continuous time counterpart, the continuous time counterpart in the time domain. So that is basically small yct. And you can see that we can multiply and divide by a factor of 2, and we can get this expression will become similar to that of cos. So we can say it will be twice XCT times cos with a factor of 2 pi by t, right? So this will be the time period 2 pi by t, and this will be the expression, final expression. Okay, coming to the last question. Now in this question, we have both an upsampler and a downsampler. We have an input that is a continuous time signal and a C2D block that samples at time period of t, sampling period of t. And we have been given this block, which is h e raised to the power j omega. Now the question says that the input is band limited. Next, we have been given what this h e raised to the power j omega is. This is basically e raised to the power minus j omega for omega less than pi by l, and otherwise it is 0 from pi by l to pi, right? And we are asked to write yn in terms of input x of n, xet. So the first thing that we need to, the first thing that is different in this question is that there is this e raised to the power minus j omega. But we have seen, so this is basically some form of a filter where there is this, extra factor. Generally, we have some gain of L, but here we have e raised to the power minus j omega. So to solve this question and to further simplify it, the first thing that we can do is we can write that block h e raised to the power j omega as two blocks. First is a low pass filter and the other is a delay. So we can say that h e raised to the power j omega is the low pass filter which has an amplitude of 1 into e raised to the power minus j omega, where this low pass filter is defined like this. It is 1 for omega less than pi by l and it is 0 otherwise from pi by l to pi, right? So as you can see here, that block h e raised to the power j omega is split into these two parts, a low pass filter and e raised to the power minus j omega. Now this is nothing, these two block, that is an upsampler and a low pass filter, is nothing but an ideal upsampler which has a gain of 1 instead of L, right? And now let's try to find out what this y of n will be in terms of xc of t. So first of all, x of n is simply xc and t. It is a continuous time signal sampled at a time period of sampling period of t. Then we pass it through this ideal upsampler to get Wn, and Wn will be nothing but, first of all, an amplitude scaling of a factor of 1 by L and a frequency scaling of a by a factor, or rather a time period scaling by a factor of L, right? That is what happens when we pass it through an ideal upsampler, right? There will be the scaling of the time period will get scaled, and also the amplitude will get scaled. And then we get Wn. Now this Wn passes through this e raised to the power minus j omega block, which is nothing but a delay of one time period. So we can say that this V of n output will be nothing but a unit delay. It will be Wn minus 1. And so if we write it clearly, it will just become xc 1 by l xc n t by l minus this t by l, which is the time period. Once we have got this Vn, we pass it through this downsampler to get y of n. So the downsampler will actually do nothing but downsample the time period again by a factor of L. And due to that, again the time period will get scaled, and right now the time period is t by L. It will get scaled by a factor of L. So the L in the numerator and denominator will cancel out, and this will become 1 by L xc nt minus t by L. So in that way, we have written yn, which is the output in terms of the input continuous time signal xc. So it's basically the input signal that is sampled with something like this. If there is a sample, there is a delay, and there is also some amplitude scaling. So with that, we come to the end of tutorial 4. Thank you.